All right, so our second titration example is going to be a little bit more challenging because we're going to worry about a diprotic or a triprotic acid. It's not going to work that much differently than one up here, but we have an extra stoichiometry thing that we have to do. We can't forget this part. So 39.42 milliliters of 0.1150 molar KOH is used to titrate 15.00 milliliters of an H3PO4 solution. And we're going to calculate the concentration of H3PO4 that must have been in that solution. So first we need a balanced equation. So now we have H3PO4, which is a triprotic acid, plus KOH, making H2O, plus K3PO4. Triprotic acid means we need 3 moles of base. That makes 3 waters and a K3PO4. So we have a balanced equation now, and we're ready to do the same kind of calculating that we did in the last example. So we're going to start with the KOH. 39.42 milliliters, and every 1,000 milliliters of KOH, there was 0.1150 moles of KOH. Now the stoichiometry step here is not a one-to-one like it was in the easier example. We have to go back to the reaction and notice that there's 3 moles of KOH for every 1 mole of H3PO4. So that converts us from volume of KOH to moles of H3PO4, and that was dissolved in 15 mils. So 0.01500 liters of H3PO4. Milliliters cancel, moles of KOH cancel. We got moles per liter of H3PO4. That's when we grab our calculator again. So 39.42 times 0.115 divided by 1,000 divided by 3 divided by 0.01500. So I get 0.1007 molar H3PO4. The polyprotic acid titrations are why you can't solve titrations just flat out using M1V1 equals M2V2, because M1V1 equals M2V2 does not have a stoichiometric step in there. There's no mole conversion in that step or in that solution style. So this is an example of a polyprotic acid-base titration.